Right, so we're carrying on this equilibrium thing. So what we do, draw a line down here and we analyze this. So we've got a negative delta H. Delta H is what? Change in enthalpy. Change in heat energy or heat or change in energy. Right. This negative sign, the negative sign or the minus sign, tells you that the forward reaction is exothermic. That means it's going to be hot. Right, so I know that this side is hot and this side is cold. Hot temperature, cold temperature, high temperature, low temperature, however you want to see it. Just remember, this side is exothermic and it's hot. Now we move on to the number of moles. So we've got one here and one here. So on this side we have 2 moles or molecules or two particles. We've got 2 on here. So now it's difficult to tell which is the high. No, I'll rephrase that. They've both got 2 molecules or moles or particles, so they're both equal pressure. So the pressure is equal in this case. Right. So a temperature of 500 degrees C, 4 atmospheric pressure, and a platinum catalyst. What did you say a catalyst was? A catalyst. Remember the 3 parts to it. So a substance that increases the rate of reaction by providing an alternative route for the reaction to take place. Okay, let's not just waffle on too much. Reaction, let's just finish it off here with a lower activation energy. Right, and is not used up, and is not used up or is chemically unchanged. Let's just bring this up. And is, let's stick to the word chemically, because I've seen this in mark schemes and it's more popular, and is chemically unchanged, as in it's not used up. I think that's probably, so yeah, and it's chemically unchanged. That's 3. So these are the 3 parts of a catalyst. If you can put all them in, you're not going to lose out. Right, so they've used 500 degrees C, 4 atmosphere pressure. ATM is atmospheric pressure. Right, okay, and a catalyst. Now the diagram shows the reaction profile if a catalyst is not used. So this bit here, the reaction goes along, energy levels rise, reactions complete, and then it dies down, lose energies to the surroundings. So just for example, if that was energy level 3, down here energy level 2, so we've lost this much energy Let me get rid of all that. Right, okay. On the diagram, draw a reaction profile when a catalyst is used. So it comes along, that's going up, below that, and then it just ends off down here and goes across there. So this bit here is, so what do we label it up as? Okay, ECAT. ECAT. Right, label the energy diagram, show the enthalpy change and the activation energy for the reaction with a catalyst. Done that. So that there is the delta H. This let me just go through that. This bit here is ECAT. Right. Then the change in enthalpy, this bit, is down here. So that there is the change in enthalpy. You can call it delta H, I suppose. Right. So that's that, and that's that. Right, a manufacturer carries out this reaction using the same catalyst. So let me get rid of this. Get rid of that, and that, and that, and that, and that, and that, and that. Right, okay, let's try this again. It's at 400 instead of 500. So we've reduced the pressure, we've lowered the temperature, and the system wants to go to the high temperature side, so it will go to the hot side. So get that right. We've reduced the temperature, so the system wants to go to the hot side, so it'll go this way. Right, okay, so we know the equilibrium will shift to the right because the forward reaction is exothermic, but they are asking for what? The rate of reaction. If you reduce so what will happen is it will reduce the rate of reaction. It's only one marker. Reduce the rate of reaction. Why? Why does it reduce the rate of reaction? Because there's less energy in the particles. There's less kinetic energy, but they've not asked us for that. Explain the effect on the yield. Right, so what did we say? You've reduced the temperature, the system wants to go to the hot side, so it goes to the right, and there's a higher yield on this side. If the equilibrium shifts to this side, if the reaction goes to this side, you get high yield. On this side will be low yield. Right, okay, there you go. Right, so the equilibrium, so the yield will be lower. There will be lower. So the equilibrium shifts. Oh, did I say lower? Oh my god, did I just say lower? Can't believe that. I'm just losing the plot. I just said higher there, and let me just get rid of that. Let's get rid of that. Can't believe I said that. It will be higher. Equilibrium shifts. So the equilibrium shifts to the right. Why? Because forward reaction is, you can't say hotter, you have to say exothermic. There you go. Right, the manufacturer then carries out this, but okay, so what's happened? So you've got 500, but they've reduced the pressure from 4 down to 2. Right, what does that mean? That means the rate of reaction decreases. So remember, we did this earlier. Let me just zoom up, see if I can find that table. It's actually quite a good table. Yeah, look at this one here. This is a perfect table to take a shot off and learn. And really what we should do is we should add another layer to this, another row to this to show the pressure. Okay, let's go back down. They're playing catch up. Whoa. So if you reduce the pressure, the rate of reaction decreases. It's not asking why. Right. Now it's the same. What happens to the yield? We don't know. It's difficult to tell. To be honest with you, it's difficult to tell because you don't know which way. Oh no, you're not in my fault. I'm reading it again, like the other question. Right. So what we want is it has no effect in this case because I thought they were changing both temperature and pressure, but they're not. No effect because you have equal number of moles or molecules, moles on each side. That's it, that'll do it. Right, okay. Not working, is it? Okay, we'll have to leave it. We'll just leave it there. Right, a mixture of carbon monoxide, carbon dioxide, and hydrogen is known in industry as synthesis gas. You convert it to methanol. Can you see that OH group there? Makes it an alcohol. And remember we said do not mix it up with OH minus, which is an ion, which is a hydroxide ion. And it's responsible for making things what? Is it acid or alkaline? Alkaline. All this stuff, put it into your head, it's just fact recall. Right, what's next? So reaction 1, you've got, this tells you it's exothermic. This negative sign tells you it's exothermic. You've got 3 moles here and 1 there, so this is the high pressure side. High pressure, so this is the hot side for both of them. Right, and then you've got 4 moles here, 1, 2, 3, 4. You've got 1, 2 here. So this is the high pressure side. And this is the low pressure side. Okay, now that's sorted. Assume that both reactions reach a position of equilibrium. For reaction 1, predict whether using high or low temperature would produce higher yield. Right. So we want high pressure because high pressure for reaction what? Reaction 1. I'm looking at pressure. Oh my goodness me, they've said temperature. Unbelievable. I think right, it's catching up. Right, okay, so sorry, they're talking about temperature. So you want low temperature because if you have, let me get this right, if you have low temperature, the system wants to go to the high temperature side, which is the product side, which is the right hand side. and that's where you get a higher yield. So because a forward reaction is exothermic. Right, for reaction to predict whether using high or low pressure would produce a higher yield. Right, so if you use high pressure, let's get this right. If you use high pressure, the system wants to go to the low pressure side, which is the side we want it to go to, the product side. So it'll shift to the right. So you use high pressure. Why? Because the right hand side of the suppose you can say there are fewer molecules on the right hand side because there are fewer moles or molecules, whatever you want to use, on the right hand side. Okay. A catalyst increases the rate of forward and backward reaction. Right, so it says it increases both of them. So, right, why doesn't it have an effect? Right, this is like a uniquely worded question, really. Right, because the catalyst increases both the forward and backwards or reverse reaction rates equally. That's equally, so overall it doesn't shift the equilibrium. Right, okay. Why does this look familiar? Right, we need to complete the energy profile diagram. Reaction profile diagram, not energy profile, reaction profile. So the reaction starts here, energy goes up, enthalpy goes up, and then so they're both exothermic. You see that there, they're both exothermic. So that means it's going to lose energy. So the products will be at a lower energy level. And then what we do is put the products there. So CH3OH. So we can just put CH3OH. So have you noticed they've not put any state symbol? So we can ignore those. Right. Draw an arrow to represent the activation energy. So look, straight line. And then from here, draw an arrow on the profile to call it E or E-act or EA. Say the effect of, if any, of a catalyst on the enthalpy change. Yeah, it will effect of the catalyst on the enthalpy change for the reaction. Of the catalyst. Where's the catalyst? Oh, okay. On the enthalpy change, right? So, okay, so be careful with that. They're saying, do you know this energy that's changed here? Is the catalyst going to have an effect? No. So there's no effect. Be careful. It took me a while to figure that one. I was trying to read it. Right. They do not want the activation energy. They don't. Look, when I first read it, I thought, oh, I thought they were on about this activation energy. They was not on about that. So you've got to be careful. They're talking about the enthalpy change. So it has no effect. Okay, that was a good question. Right. The flow diagram shows the main stages. Give the name. Okay, we don't. This is not in the new spec, so we don't have to do this. Call the Haber process. gas A obtained from air is nitrogen, and from natural gas is hydrogen. State the purpose of the condenser. Right, so condensers here, you react them and you produce what? Ammonia. So you condense it. To condense or liquid, well, right, that would be a poor choice of words, to condense, because they put the word condenser there. To liquefy the ammonia. Okay, name the catalyst used in the reactor, in the reactor. So it's iron. Again, you don't have to know this anymore. Suggest why 2 reasons on reactor. Right, okay. It saves raw materials, you're not wasting them, and it saves, uses less energy, and you can also say it sort of help produce more, to help produce more what? Ammonia. Okay, here you've got aluminium, not aluminium, what I'm talking about, ammonia being produced at different temperatures, and these are different pressures, atmospheric pressures. State the conditions of temperature that would produce the largest percentage of yield. It would be 400, 350. So here, and that's your percentage yield. So it's 400 atmosphere pressure, and at 350. Yeah, so 400 atm atmospheric pressure and 350 degrees Celsius. Right, okay. Let's grab that. Get rid of that. Right, okay. Find the percentage yield of ammonia, which is 200 atmosphere, 450, that's up here. About 40%. Yeah. Suggest why the industrial process, the percentage yield of ammonia at 200 atmospheres and 450 degrees is only 15%. Right, okay, it should be 40. It should be 40, but it's only 15 degrees, right? Okay. And the answer they've given, the reaction does not reach equilibrium. Right? Phosphogyne. Okay, let's see if we can squeeze this in. Right. Phosgene. Right, okay. We'll do that again once more. Split that up. Negative delta H tells you that this is exothermic. If this side is exothermic, this is hot, and this will therefore be cold. Then we look at, you've got 2 moles here and 1 here. So this is the high pressure side, and this is the low pressure side. Right. The reaction mixture is kept at temperatures between 50 and 150. If a temperature above 200 is used, only a small amount of phosgene is formed. Suggest why only a small. Right, because the equilibrium shifts to the left because the forward reaction is exothermic. Predict how yield of phosgene will change if the reaction is carried out at high pressure. Higher pressure. So if you have high pressure, the system wants to go to the low pressure. Right. Yield. So right. Okay. Let me get this right. So this is. I always miss this. Oh, that's not good, is it? What happened there? Yield. Right, because it's asking for yield. At higher pressure, the system wants to go to the low pressure side, which is forward. So the yield would increase because there are fewer moles or molecules on the right hand side. There you go. Phosgene reacts with water to form hydrochloric acid and CO2. Right, let me have a look at phosgene. What was it? Phosgene is COCl2. So they're saying if I react COCl2 plus water, you end up with hydrochloric acid plus carbon dioxide. Now we need to balance them somehow. You got one carbon, two chlorines, so we need two chlorines. You've got two hydrogens, two oxygens. Okay, that's it, that's balanced it. Right, we need to draw a dot. Right, okay, we won't bother with that. Dot and cross, we can do that some other time. Right, okay, we'll call it quits at that for this one. Let's have a look. 1, 2. Okay, that'll make a nice end to the next video. Okay.